Ever really stop and think about what's actually happening inside your phone's processor? I mean, we're talking billions of tiny switches, flipping trillions of times a second. How on earth does that not just collapse into pure chaos? Well, that's exactly what we're going to get into. So, how do you get billions of transistors to act in perfect harmony? It's like trying to conduct the world's biggest, fastest orchestra. Well, it turns out there's a single conductor for the whole show: the system clock. Think of it as the relentless heartbeat of the chip. Every single part moves to that one single rhythm. All right, here's what we've got on tap. We're going to start with that internal clock, then get into the actual rules of this crazy relay race. After that, we'll meet our star runners, these things called flip-flops and latches, and see what kind of glitches they have to dodge. And to wrap it all up, we'll take a peek inside the engineer's playbook to see how they pull it all off. Okay, so like any high-stakes race, this one has rules. And I mean strict, non-negotiable rules. These aren't just friendly suggestions. They're basically the laws of physics that keep a multi-billion-dollar chip from becoming, well, a very, very expensive paperweight. So let's meet the key players here. The best way to think about this is like a relay race, right? The data is the baton. Setup time is basically the rule that says the next runner needs to have their hand ready before the baton arrives. Then you've got hold time. That's the rule that says you have to firmly grip that baton for just a split second after you get it before you take off. If you mess up either one, you drop the baton. Simple as that. And this is where we see what happens when things go wrong. If you break the setup rule, basically you're too slow, the next runner ends up grabbing the old data from the last lap. Not great, but maybe you can recover. But breaking the hold rule? Oh, that's a total disaster. That's what we call a race condition. It's like the runners crashing into each other. The data gets corrupted, and the whole system just goes haywire. All right, we've got the rules down, so now let's talk about the runners. The actual circuits that are passing this data baton back and forth. In chip design, you've basically got two main types of athletes for this race, and believe me, they have very different styles. First up, you've got the flip-flop. I want you to picture a super disciplined sprinter. It only acts at one precise moment, that go signal from the clock. It's reliable, it's predictable, it's safe. But then you have the latch. This one's more like an agile acrobat. It's level sensitive, which is a fancy way of saying it can become transparent, letting data just flow right through it for a short window of time. Super flexible, but that flexibility comes with some serious risks. And here's why that difference is so important. Look at the flip-flop on the left. If the data shows up even a little bit late, that's it, game over. It missed its window and the race fails right there. But now look at the latch on the right. Because it can become transparent, it can let that late data just slip through. It's literally borrowing time from the next part of the race. This little trick can turn a catastrophic failure into a win. It's an incredibly powerful technique, but man, is it tricky to get right. Now, it'd be great if this race was run on some perfect imaginary track. But it's not. This is the real world, and physics loves to throw a wrench in the works. There are all these hazards that can trip up even the most brilliantly designed circuits. And honestly, engineers build entire careers around figuring out how to navigate these glitches. So one of the classic hazards is something called clock skew. Imagine all our runners are spread out across a giant stadium. When the starting pistol fires, who hears it first? The runners right next to the gun, right? The ones way on the other side of the field hear it a split second later. That's clock skew in a nutshell. Different parts of the chip get that ghost signal at slightly different times. And that tiny delay, it eats away at your precious time for doing actual work, making the whole race that much tighter. Okay, this brings us to a really weird and frankly dangerous question. We've talked about how the data has to be stable before the clock signal and stable after the clock signal. But what if it changes at the exact worst possible moment? Right in that tiny, forbidden zone. The answer is this truly bizarre state called metastability. When you break those timing rules in just the wrong way, the output of the circuit can get stuck. It's not a 0 and it's not a 1. It's just hovering in between in this weird digital limbo. And the scariest part? It can stay stuck like that for a totally unpredictable amount of time. Probably the best way to picture this is the classic ball on a hill analogy. Think about it. A stable state, a 0 or a 1, is like the ball resting safely in a valley. But a metastable state, that's like balancing the ball perfectly right on the tippy top of the hill. You know it's going to fall one way or the other, eventually, but the time it takes to actually decide and roll down, it's theoretically unbounded. And that kind of
Maybe eventually uncertainty is absolute poison to a system that needs picosecond precision.
Okay, so we've got these strict rules, we've got our different runners, and we've got all these real-world hazards. How in the world do engineers actually make the right call? How do you design a chip that's both screamingly fast and rock-solid reliable? Well, like so many things in engineering, it all comes down to trade-offs. And this table here is basically the engineer's cheat sheet. You can see the trade-offs laid bare. Flip-flops, they're your default choice. They're safe, they're simple, but they're not the absolute fastest. Then you've got transparent latches. They're amazing at borrowing time, which can make your chip faster, but they have a much higher risk of those catastrophic hold time failures. And then you have the speed demons, pulsed latches, lowest overhead, pure speed, but they come with a massive risk. It's this constant, delicate dance between raw speed, power consumption, and just basic safety. When you boil it all down, it leads to one simple conclusion. In the world of microchips, timing isn't just an important thing. It's everything. It's the invisible architecture that makes our entire digital world work. From the watch on your wrist to the most powerful AI servers, every single one of them relies on winning this ridiculously fast relay race, billions and billions of times every single second. So I'll leave you with this final thought. Now that you know the rules of the race, the players, and the very real risks involved, what would you do? If you were designing a chip, would you prioritize the raw, blistering speed of a latch? Or would you go for the simple, predictable safety of a flip-flop? There's no single right answer, but grappling with that question, well, that's what makes a great chip designer.